Okay, this slideshow goes through some of the key ideas that you should know from GCSE, plus that new stuff on nomenclature, naming different compounds. Now, the first thing to make sure you absolutely know are the types of formula. I'm going to just put this one at the bottom here in brackets, skeletal formulae. We won't cover those for the moment. You can have a little look. I'm sure you'll understand it if you look at it, but we won't cover that until we actually do A-level. Molecular formula should be really straightforward for you by now, so it just tells you the actual number of atoms in each formula. We tend to use that all the time in inorganic chemistry, whereas in organic chemistry it's much more important to know the structure of the molecule. Empirical formula used a lot with moles. Again, we don't use it loads in organic chemistry, so less important. General formula you should know from GCSE that the alkanes are CnH2n plus 2. So that means if you know the number of carbons, so say 2, then to get the number of hydrogens, you would double the number of carbons and add 2. So if the number of carbons was 2, then the formula would be C2H6, because 2 times 2 plus 2 is 6. For alkenes, more straightforward, CnH2n, so C3H6, C4H8, etc. Structural formula, so these two are the ones that we use the most in organic chemistry. The structural formula is really useful because it shows the connectivity in a simple way where you don't need to draw all of the hydrogens, which is a bit annoying to draw the bonds between the carbons and the hydrogens. It takes a long time, but it shows you just as much. And the displayed formula, you have to show all of the bonds. So notice this one, the OH bond, that's the one that students often leave out, and they would just draw all of the bonds except the one between the O and the H. So just be careful not to make that mistake. More frequently, you will see that we often use a hybrid of the structural and displayed formula. And that's just because it's convenient. And that's perfectly acceptable if you're asked to draw the structure of something. But you should take note of the wording, because if you're asked for the structural formula, you have to draw the structural formula. If you're asked for the display formula, you have to show all the bonds. And when you're naming molecules, you should immediately be looking at the functional group. So the functional group is the part of the molecule that determines how it reacts. So for alkenes, it's the double bonds, how a molecule reacts. And it's the functional group, the fact that every molecule in a homologous series has got the same functional group. That's why all the molecules in the same homologous series have similar chemical properties, react in the same way. So for alkanes, the nature of the functional group, well, it's just single CC and CH bonds. They're strong bonds, and that's one of the reasons why alkanes are not very reactive. They're only really used for fuels. Alkenes, it's the CC double bond. So you'll notice I've made sure each of my carbons has still got 4 bonds, and I just haven't drawn what's connected to them. So if I was drawing the actual molecule, I'd draw the bits connected, but if I'm just showing the functional group, I draw it like this. A halogenoalkane, you came across at GCSE when you looked at reactions of alkanes and alkenes with bromine. And it's just where you've got an alkane with a halogen atom substituted. Okay, so alkane with halogen atom substituted. And that's a halogenoalkane. You can also get dihalogenoalkanes where you might have 2 halogen atoms instead of hydrogens from the corresponding alkane, and we'll look at those a bit later. Alcohols, OH group, not much more to say there. Carboxylic acids and esters, slightly less important for now, but you did come across them at GCSE, and we will look at them again at A-level, so you should recognise them. Again, important thing to notice, carbon always has 4 bonds because it's group 4, valency 4. Oxygen always has 2 bonds because it's group 6, valency 2. So I've got a blank bond there that would join to the rest of the molecule. Hydrogens always have 1 bond because valency 1. And whenever you draw a molecule, you should just double check that you've got the right number of bonds for everything. Okay, so key principles of naming. I've got 4 questions really that I run through every time I name a compound. And the first one is, which functional group have I got? And that usually determines the suffix, the ending. So if it's an alkane, it will end in -ane. If it's an alkene, it will end in -ene. Some functional groups will have prefixes instead. So we're going to do an example, and that's the halogenoalkanes, where you put the halogen at the front. So e.g. chloro would go at the front. So watch out, they can be suffixes or prefixes. The ones we've come across so far at GCSE were suffixes, so ol, ain, een, but we will come across prefixes at A-level. How many carbons in the longest carbon chain? That's really important because that determines whether it's meth, eth, prop, etc. And you should know those numbers. So meth, eth, prop. 4 is bute, 5 is pent, 6 is hex, 7 hept, 8 oct, 9 non, 10 dec. Do I need a number for the functional group? So that will be, could it be in a different position? So with the double bonds, often the answer is yes. Yes, it could. And the same with the halogen atoms. They can often be on different carbons, on a different atom, different position. Are there any branches? So that was the things that we saw, like the methyl group. So methyl would be a CH3 joined on in the middle somewhere. Ethyl group would be a C2H5 joined on to the middle somewhere, and you could keep going down and down, but methyl and ethyl tend to be the most common branches that you might see. And again, those will usually need a number because they could well be off the second carbon or the third carbon. They'll never be off the first carbon, because if they are, they're just extending the carbon chain, and therefore you would just change your name to, if it was prop, it would actually be bute. So branch is always off middle carbons. Okay, so I'm going to introduce the idea of structural, or remind you of the idea of structural isomers very quickly before we look at some examples. And you know from GCSE that they're molecules with the same molecular formula but a different structural formula, i.e. they're connected up differently. Okay, so key thing, same molecular formula, connected up differently. Okay, we're going to start by logically working through the structural isomers of hexane. I'm going to show you how I would work through it, because I think you should apply the same method as you do different isomers. So hex means 6 carbons in a row. So I'm going to draw my 6 carbons in a row to start with. 1, 2, 3, 4, 5, 6. And ane means each of those is surrounded by a hydrogen. So this would be a displayed formula that I'm drawing. So that's my first molecule that I'm kind of using as my starting point. Okay, now there's no functional group that I can move around, so I have to look at branches. So the most straightforward thing to do would be to take one CH3 group from the end and move it. So let's take CH3 from the end and put it somewhere else. So rather than having it on the first carbon, let's put it on the second carbon. So now I'm going to have a chain of 5 in a row, 1, 2, 3, 4, 5, and I'm going to put my CH3 on there. Okay, and I can see straight away, I haven't drawn on all my hydrogens. That one would need 3, that one would need 2, 1, this one would need 2, etc. Because remember, our valency of carbon is 4. Okay, so that would be my first isomer where I've moved the CH3 group to the second carbon. And then I just work along. Could I put it on the third carbon? Well, yeah, I could. That would be different to the molecule before. So let's do that. 1, 2, 3, 4, 5 again. And instead of having it on the second carbon, I've just moved it along one. And then I'd fill in all the hydrogens. I'm not going to do that for the sake of time. Okay, so now I've moved one CH3 group. The next question is, could I move it onto the fourth carbon? Well, I could, but if I did that, I'd have exactly the same molecule as this, just flipped over. And remember, because molecules are dynamic, they're constantly rotating and turning, there's no left-hand side or right-hand side. So if I just had it on the next carbon along, well, those two would then be the same thing. So that wouldn't be another isomer. Okay, so since I've done all my options with one, the other one that you might think is, could I have put it above the carbon instead of below? Well, again, that would just be twisting the molecule round. So no, the answer is no to that. Okay, so next one, I'm going to move 2 groups at the same time. So let's move 2 CH3 groups and put them somewhere else. So now my longest carbon chain is going to be 4 because I've taken 2 groups off, 2 carbons off. And let's put a CH3 on there, and I could put another CH3 on there, and that would be a different molecule, wouldn't it? Or would it? No, it would. Okay, so I've got 2 on the same carbon, so that's a possibility. Or I could have done 1, 2, 3, 4, and put 1 off the second carbon and 1 off the third carbon. I couldn't, just like we did before, I couldn't have put both off the third carbon because that would be the same as this molecule just flipped over. I couldn't have put them the other way around, so 1 underneath on the second and 1 on the top is on the third, because again I'm just flipping the molecule over. So you need to just make sure that you're thinking through the different rotations. So 1, 2, 3, 4, 5 molecules. I can imagine that you might ask the question, what about an ethyl group? So let me draw you 4 and then draw an ethyl group coming off the second carbon. So imagine you tried to do that, and now let's have a look at what we've actually drawn. So that's an ethyl branch, it looks like, coming off the second carbon. But now if I trace the longest carbon chain, I've actually got 1, 2, 3, 4, 5 with the carbon off the third, the branch off the third. So all I've drawn is this one here. So those 2 that I've just highlighted would be identical. So it isn't possible to have an ethyl group for this particular example. Okay, let's go on to naming them now. So this I've just taken from the internet, the diagrams, just to make it all a little bit clearer. Now, functional group is ane, so I could start straight away by writing ane. So I'm going to follow my questions through. How many carbon atoms in the longest carbon chain? Question 2, 6. So that gives me hex. So hexane. Do I need a number for the functional group? No. Are there any branches to name or number? No, for this one. Okay, so we've got hexane straight away. Let's follow through the same method for the next one. So what's the functional group? Well, still it's saturated hydrocarbon, so it's ane at the end. Then how many in the longest carbon chain? Well, there's my longest carbon chain, 1, 2, 3, 4, 5. So it's based around pentane. Then do I need a number for the functional group? No, not for alkanes because there's no functional group. Are there any branches to name or number? Yes. So firstly, to name, it's methyl because it's a CH3 group. There's only 1 carbon in the branch. So it's based around methyl pentane. Do I need to number it? Well, that depends on whether there's another possibility. Well, yes, there is, because here I've got it on the third carbon, so I do need to number that's carbon number 2. So it's 2 methyl pentane. Notice no commas or anything between words and no spaces between words, but you always have a dash between a number and a word, and you would always have commas between 2 numbers. Okay, this one I follow through the same thing. So functional group ane, longest carbon chain, pent, branch is methyl, and the number this time is 3 methyl pentane. So I often end up writing them backwards or in strange orders. It doesn't matter. Don't try and work out the whole name in your head and then try and write it down. It's much easier this way. Okay, we'll keep going. So I've drawn hexane as my original here, just as a reference for us. Now my next logical thing was to take 2 CH3 groups. We've got a first one. Which functional group? Still ane. Oh, that's an E. Longest carbon chain. Okay, 4 in a row. So it's going to be based around bute. Do I need a number for the functional group? No. Are there any branches? Yes. So there's 2 methyls. So I'm going to write methyl, and I'm going to write dimethyl. So di means 2 of the methyl groups. And then do I need to number them? Yes, because they don't need to both be off the second. I could have 1 off the second and 1 off the third, which is what I've got over here. And so my numbers are 2, 2 dimethyl butane, because that's carbon number 1, there's carbon number 2. Whereas this one, same idea, functional group ane, longest carbon chain, bute, number of methyls 2, so dimethyl. What are the numbers? 2 and 3. Okay, and notice I could have numbered from either end, so I could have had 1, 2, 3, 4. It would have been exactly the same. It's always going to be 2, 3, whichever way I count that one. So that's structural isomers of hexane. So on to how alkanes like hexane hexane, sorry, react with bromine. So you learnt at GCSE that you could do these substitution reactions where a bromine atom would replace a hydrogen atom in the alkane. But as we already said, alkanes are really unreactive, and so we need quite severe conditions to make it happen. So we have to have bromine as a liquid, has to be in liquid form. We can't have aqueous conditions, and we need UV light. And what actually happens, and you'd learn this at A level, and we'll look at the reaction in lots of detail at A level, is the UV light actually breaks the Br-Br bond, and we end up with these very reactive Br atoms. Okay, so you get two Br atoms, and they're really reactive because each one's got 7 electrons in the outer shell, and they're called radicals, free radicals. You don't need to know that for the moment, but it means that they then will go on and attack virtually anything. So that's the only way we can get the alkanes to react with the halogens. The colours underneath are important because this is what you would observe. So alkanes are colourless. Notice colourless, not clear. Bromine liquid is this red-brown colour, probably actually a bit darker in real life than I've drawn here. Our bromoalkanes are colourless. Hydrogen bromide, which is a gas given off, a corrosive gas, quite nasty, you'd have to do this in a fume cupboard, is colourless. So as you do the reaction, the observation would be the red-brown colour disappears. Red-brown colour disappears. So let's look at a couple of examples. Nice GCSE example. Let's just start with, well, we could start with CH4, but let's do ethane, C2H6. Okay, so all that happens, it's got the Br, single covalent bond between the two. Bromoalkane in this case, so we just need to swap one hydrogen for one bromine. So I'm going to put it there, but it actually doesn't matter. You could swap anywhere on the molecule, but every position would be identical on this because remember it freely rotates and turns all the time. So plus HBr. So all I've got is this switch between this hydrogen and this bromine. So this hydrogen, this bromine. Okay, a more complicated example then. Let's do something that is a bit longer. So propane. Displayed formula, so all of the bonds. Here's our bromine, so the UV breaks that bond to form those really reactive free radicals, and now there's a few possibilities for, or a couple of possibilities for what we could have as our bromoalkane, because it could substitute on this first atom, so I might have my Br there with all the rest H's, or it could have substituted on this second atom, couldn't it? It could be either way. So we've got two possible isomers, and in fact both would be produced. This is mono substitution because we're talking about one hydrogen being swapped for one bromine atom. Okay, and we'll look at some of these isomers in a second. So imagine that we'd started instead of with propane, which was the one I just did where we had two isomers. Imagine we started with butane, C4H9Br, so sorry, C4H10, and then we switch one hydrogen for a carbon. So here's our C4, and let's just logically work through the possibilities. Let's start with a Br on the first carbon. That's going to be the first possibility, isn't it? And then let's see whether we can move that around. We could move it to the second carbon, couldn't we? And that would be a distinct molecule, a different molecule. We'd have to break a bond in order to convert the first one to the second one. So that's a structural isomer because they're connected, they're bonded differently. Okay, so there's a second structural isomer. If I put it on the third, well, that's no different to the first, to this same one again, is it? Because it's just flipped over. If I put it on the fourth carbon, that's the same as the first one. So then my next stage is, could I have some methyl groups? Well, I could. Let's take off the methyl group on the end, which means that I've now only got 3 carbons in a row. Let's put the Br on here. And now I'm going to need to have my CH3 on there. Okay, and it can't be at the end, can it? I can't just bend it round. For it to be a branch, it has to be off a middle carbon, and in this case there is only one middle carbon here. So I could do it like that, or I could have my bromine on the second carbon with my methyl also on the second carbon. So there are my 4 possible isomers. So let's see if we can name those. And it's going to be the same idea as before. So first of all, functional group. Well, in a way I've got 2 because I've got saturated substance, so it's going to end in ane, but I've also got my halogen, and that's, we've already said, is a prefix, so it's going to be bromo at the front. I think I'm going to run out of space here. Bromo, and the end is going to end in ane. How many carbon atoms in the longest carbon chain? 1, 2, 3, 4, so it's based around bute. Do I need a number for the functional group? Well, yeah, I do, because I can have it on carbon number 1 or carbon number 2. So this is 1 bromobutane. Okay. Are there any branches to name or number? No. Let's do the next one. I'm going to use a different colour because that wasn't very visible. Same thing again. So saturated going to end in ane. Bromo is the prefix because that's my functional group. Longest carbon chain is 4, so bromobute. And then, do I need a number? Yes, 2 bromobutane. Okay. Right, let's look at this one here. So now, slightly different. Functional group is still ane, and it's still bromo at the front. So can I give myself a bit of space? How many in the longest carbon chain? 3, so that's prop. Do I need a number for the functional group? Yes, I do, because it could be on the second one. So it's 1 bromo something. Are there any branches? Yes. So I need a methyl. And does it need to be numbered? No, because it can only be off the middle carbon. So 1 bromo methyl propane is the name. Notice when you've got things that always go as prefixes, so the branches and the bromo go as prefixes, you do them in alphabetical order. So B is earlier in the alphabet than M, so it goes at the front. Let's do this one. This one, same idea. So ane, bromo at the front, prop, 3 in a row. Do I need to number the functional group? Yes, so it's 2 this time because it's on carbon number 2. And then the methyl, which I don't need to number because it couldn't be anywhere else. So 2 bromomethyl propane. So they look like quite complicated names, but actually if you work through those 4 stages, you will get to the answer without too much trouble, hopefully. Okay, that was a bit more space to do some more. Reactions of alkenes with bromine then. Now, alkenes are much more reactive because they've got that double bond, and that double bond means there's 2 pairs of electrons in there, so it's quite attractive to other reactants that are coming towards it. And it's also possible to open up that double bond. You don't have to break the whole double bond to get the molecule to react. You can open up just one of, you can break just part of it. And so alkenes are much more reactive. And so rather than having bromine liquid, we can have it under aqueous conditions. And we don't need UV light. Okay, so there's nothing added. So this is actually just done at room temperature, and you can just do it in a test tube reaction. And it's a really useful, quick test for unsaturation, i.e. double bonds. So really quick and easy test for double bonds. And also for triple bonds, but double bonds. What would we see? Well, the observation would be orange bromine water. Notice it's not red-brown this time, so it's not bromine liquid, it's diluted down. So orange bromine water turns colourless. Again, not clear. It's actually a clear solution to start with, just an orange one. So make sure you say colourless at the end. So orange bromine water turns colourless, or you might have used the phrase that alkenes decolorize bromine water. That's still perfectly acceptable at A level to say it in that way. And this is an addition reaction, because let's have a look at what happens. So we'll take ethene, most straightforward example, Br2. And what happens is our double bond opens up, so now it's a single bond, and each carbon needs to have 4 bonds. So now there's a spare on each, which the bromines attach onto. So it's addition because all you're doing is you're adding together 2 molecules and you're making one kind of total molecule. And this is a dibromo alkane because there's two Br atoms on it, so we could name it. So we've got ethene, obviously bromine, and here we have got, well, think, do we need to number? So we'll go through our 4 questions. Functional group, well, it's saturated, so it's ane, and it's going to have bromo at the front, and it's going to have dibromo because there's 2 lots of them. Are there any branches? Oh, sorry, second question, how many in the longest carbon chain? 2, so it's eth, so it's dibromoethane. Are there any branches to name or number? No, but we do need to number these because you could have an isomer of this where both the bromines were on the first carbon, couldn't you? So this is 1, 2, dibromoethane. So notice comma between the numbers if you have 2 numbers, and then a dash between numbers and letters. Okay, so let's look at our C4H8 example. So imagine we had butene as our reactant, 4 carbons in a row. So this would be butene. Notice what I'm doing here. I'm being careful to make sure I've got 4 bonds for each carbon. People often draw on too many hydrogens or somehow end up with a carbon with only 3 bonds. Just be careful, just look through. So which functional group? Ene is our functional group, so it's a suffix one. How many carbons in the longest carbon chain? 4. Do I need a number for the functional group? Yes, because it's on carbon number 1, but it could have been on carbon number 2. So but1-ene. Are there any branches to name or number? No. So that's the name of that one. Another one. Let's do the same thing, but just move the functional group up 1. I'm not going to draw on all the hydrogens, but I've drawn on all the bonds so you can see where they'd go. And that would be but2-ene, because which functional group? Ene. How many carbons in the longest carbon chain? 2. Do I need a number for the functional group? Yes. And it's 2. And I can't have but3-ene because that's the same as but2-ene. I can't have but4-ene because that's the same as but1-ene flipped over. I could have some branches, so I could take off my CH3 and put it in the middle somewhere. Let's see whether I've got space for that on the next page. But if not, I would just do it in the same way as before. I know I don't have space. Okay, let's look at these dibromo alkenes. So if we reacted but1-ene or but2-ene with bromine, we would end up with our dihalogenoalkane. So let's try and draw it 4 in a row. Let's put Br and Br on there, and then the rest are going to be hydrogens. 1, 2, 3, 4, 5, 6, 7, 8 hydrogens, 2 bromines. I haven't drawn them all on, but I think we know what we're doing, don't we? So which functional group? Ane, because it's saturated. Also bromo, dibromo, because there's 2. How many carbons in the longest carbon chain? 4. So dibromobutane. Do I need a number for the functional group? Yes, because I could have them on any combination. So it's going to be 1, 2, dibromobutane. And there's the name of that one. Okay, let's be systematic and just move the carbons around. So let's put them off these 2. Okay, now that one would, same idea, ane, dibromo, but, and then number this time 2, 3. Okay, I could shift the 2 along another one, but if I did that, I would just have 1, 2 dibromo just flipped over again. I don't know if I've left another. I haven't left another page on here, so I can't draw any more. But there are some other options. I could have 2 bromines on the first carbon, so I could make 1, 1 dibromobutane. I could have 2, 2 dibromobutane. I could have 1, 3 dibromobutane. I could have 1, 4 dibromobutane. It probably would be worth you having a little look and seeing whether you could rearrange them. Let's just have a look at one more for if we had a methyl group attached. So if I take methyl group off and put it in the middle there, and let's just put that like that. So I'm just choosing at random really. There are different options, but we use the same thing through, same method. So which functional group? Ane at the end, dibromo as a prefix at the start. How many carbons in the longest carbon chain? This time only 3. There, prop. Do I need a number for the functional group? Yes, because the bromines could be anywhere. So I need 1, 3 dibromopropane. Are there any branches to name and number? Yes. I need a methyl branch. and I don't need to number it, because there's only one possibility. If it's propane, there's only one middle carbon it could be on, so I don't need to write anything else. And that's it really. Alphabetical, the B is the bit to look at rather than the D for di. So B for bromo goes ahead of methyl, and we're done.